Look up during the day and you'll see either overlooming clouds or a clear blue sky, or something in between. Look up during the night, and if the sky is clear enough, you'll see further beyond our own planet. You'll see our view of space. Space is full of many things. So many things that we know about, but also things that we don't know about. It's also full of nothing. Space is considered largely empty, but also full at the same time. Space is full of different planets, comets, asteroids, nebulas, galaxies, all these within what we perceive as the universe. And one aspect that's always been present within our planet's lifetime: stars. Stars are everywhere, and they are central to many of the ideas and teachings we have of the space around us. They represent the fundamental building blocks of our galaxies. By just taking a look at the age, distribution, and composition of stars, can let you trace the history, evolution, and dynamics of that galaxy. Stars are something outside of our planet, and nearly everyone has seen at least one, be it the stars of the night sky or the one star that brings life to our planet, the sun. Ancient cultures didn't just look up at the sky to see the stars, they observed them. They identified different configurations we know as constellations, and tracked their movements. These constellations could be used for farming, charting courses across the sea, and other applications as well. There are tons of constellations like Cassiopeia, Orion, Ursa Minor, Canis Major, and many, many more. Nowadays, astronomers like to use constellations as guideposts for naming newly discovered stars. It's also used as a tool for navigation, like the Southern Cross constellation in the southern hemisphere, or the North Star in the northern parts of the Earth. So, how is a star formed anyway? Throughout most galaxies, stars are born from the clouds of dust that they contain. These are often called nebulas, and mainly contain gases like hydrogen, helium, and other ionized gases. With the gases, the nebulae also contain dusts of sorts. You've probably heard of nebulas before. They're often depicted as these very pretty clouds that are just floating in space. A famous section of the Eagle Nebula is the Pillars of Creation, captured by the Hubble telescope. The blue represents oxygen, red, sulfur. Green is both nitrogen and hydrogen, and it stretches about 4 to 5 light years. The Eagle Nebula itself is around 70 by 55 light years.
These stars are formed in molecular clouds. The molecular clouds are large regions of gas. Many of them, in fact, much of the molecular gas is in so-called giant molecular clouds, which can have sizes up to 100 parsecs, or that's 300 light years in size. And this gas is dense by interstellar standards, can have densities of thousands of particles per cubic centimeter. They're very dusty, that is, they have tiny particles which absorb light. And that's very important because, first of all, the molecular hydrogen in these molecular clouds is actually formed on the surface of these dust grains. And secondly, the dust grains tend to block the ultraviolet radiation which could destroy the molecular hydrogen. So it's very important for the gas to be able to be shielded like this so that it can be molecular. So first let me talk about how low mass stars like the sun, for example, form. What you need to do is you have to have a region of gas in which the force of gravity can exceed the forces associated with pressure. So an easy way to think about this is just in terms of energy. I can just ask, if I look at a region of gas, I calculate its gravitational energy, and I calculate the energy that it has in thermal energy, just due to its heat, then I can say, well, which one is bigger? If the gravitational energy is bigger, then at least in principle, I can go ahead and undergo a gravitational collapse. And I would start off as I mentioned, at a density that's measured in particles per cubic centimeter, and then by the time you actually form a star, you have densities measured in grams per cubic centimeter, 24 orders of magnitude larger than in particles per cubic centimeter. So one of the things that happens, though, is that while this gas is contracting, it also has some angular momentum. So just as the classic example of an ice skater who is spinning on the ice with her arms outstretched, as she draws her arms in close, she will spin faster and faster because you conserve angular momentum. Similarly, if I have a gas cloud, and even though it's rotating very, very slowly, as it contracts, it too will spin up. And as a result, while you will get a central star, you'll also get a disk of gas around that. And in fact, much of the gas that feeds into the star might first fall into a disk and then gradually accrete from the disk through the disk onto the star. And this disk toward the end of the formation of the star is very important because that is the site of planet formation.
The process of a birth of a star is by no means fast. It can take millions of years to grow, and a star the size of our own sun requires about 50 million years to mature from the beginning of the collapse to adulthood. This Hertzsprung-Russell diagram is sort of the periodic table of stars. The main sequence is where about 90% of all stars lie, and they span across a wide range of different luminosities and colors. The smallest of the main sequence, the red dwarfs, may contain as little as 10% of the mass of the Sun, and are by far the most numerous stars in the universe. And because of their smaller size, they can last tens of billions of years. On the other side of the main sequence are the hypergiants, which can be 100 or more times larger than the Sun, but only have lifetimes of a few million years. Today, hypergiants are extremely rare, with the entire Milky Way galaxy only containing a handful. Main sequence stars require nuclear fusion to prevent the collapse of its own weight coming in on itself. The nuclear fusion of hydrogen converting to helium produces an immense amount of energy. This output of energy provides enough pressure to keep the star from collapsing under itself. But after a point in time, this energy runs out.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table. What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker, and actually the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula, and they're some of the most beautiful objects in the universe. A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
When a star's life reaches its end, it turns into a white dwarf. Why doesn't the white dwarf collapse even further if there's no nuclear fusion? Well, simply, the pressure from the electrons moving prevent it from collapsing, but this can only hold up to certain sizes. If a white dwarf is close enough to another star, the gravity of the white dwarf can drag matter from the outer layers of the other star onto itself, causing a burst of nuclear fusion. This burst causes the white dwarf to expel its remaining material and brighten substantially, and this cycle continues until the white dwarf is no more. This is what people call a nova. If the white dwarf is large enough, instead of just having the surface of the white dwarf explode over time, The entire core collapses on itself, then explodes in what is called a supernova. Because the white dwarf is large enough, the core slowly goes down the periodic table. It converts hydrogen to helium, then helium to lithium, lithium to beryllium, beryllium to boron, and so on, all the way until it reaches Fe, iron. Once a core reaches iron, it means that the star has sucked all of the energy that it has, because going any further down actually uses more energy than it creates. Then the core shrinks from thousands of miles wide to only a few dozen, and because of this, the temperature spikes immensely, and this rebound releases an unimaginable amount of energy that results in the supernova. If the size of the cores that collapsed are even larger, they can produce neutron stars at the center of the supernova. These neutron stars are very small, only around 18 miles wide, and normally have a very high density. Like their name, they are composed of closely packed neutrons. And if the size of the core is even larger than that, it can produce even a black hole. The dust that remains after the novas and supernovas end up creating new nebulas because the dust blends in with the interstellar gas around it, and these get recycled and form new stars. And from this, the cycle of stars continues.